So let's go back a little bit and try to understand. Let me try to summarize what we would like to do, what we want to do. We want to construct the theory of a simple normal fluid. A simple normal fluid means that the fluid that has a particle that you can think about that as a gas, a liquid of particles with the same mass, the same type of particle with mass m, the same mass, the simple. These particles do not have internal degrees of freedom, and they are the same. And the theory, we assume that there is, we will see, this is important, there is no spontaneous symmetry breaking. It's the normal fluid, in contrast to superfluid, which will be discussed later. We want to construct the hydrodynamic theory. So hydrodynamics means theory that can describe the behavior of this collection of particles at large distances and large time scales. And we want to have a discussion that is as general as possible and based on only general principle. And try to avoid physical prejudice, as we would see. So surprisingly, that's not a trivial task, though it can, as we will see, it can be done, but it has to be done in several steps. So some of the first step, let's try to see if we follows the philosophy of hydrodynamics, what would be our first steps. So the first step would be to identify our hydrodynamics degrees of freedom. And in our case, these are just the density of conserved quantities. So density of particle number, density of momentum, density of energy. And this is energy density. And n is the particle number density. Second step, we would write down the conservation laws. Derivative of the particle number plus gradient of the particle number flux is 0. Derivative of the momentum density. So here I would like to write 3 equations, one per component, plus derivatives. So let me write carefully this way: ij with indices equal to 0. So here is pi. ij is the flux of the ith component of momentum along the x direction, along the y direction, j direction, sorry. So if we have momentum, this is the flow of the ith component of the momentum along the y direction. And the last equations, I would write like this: d epsilon over dt. Here, for a reason that for simplification of future notation, I write this epsilon as a capital epsilon plus derivative of the energy current is equal to 0. So these would be our second step, and the third step would be to write down the constitutive relation equations that relate these flux. This flux is the flux of particle number, the flux of momentum, and the flux of energy in terms of the density, in terms of the hydrodynamic variables like n, pi, epsilon, or their thermodynamic conjugate. Okay, and in the third step, we need to satisfy certain conditions, Onsager, positivity of entropy production, etc. So these turn out to be further constrained. The third step is further constrained by Galilean invariance. That imposes certain restrictions and eliminates some possible terms that we could have written down without knowing about the Galilean invariance. So Galilean invariance is transformation from, say, the lab frame to some lab frame that we call that K, to a frame K prime that move with velocity V. Let's call that K prime move with velocity capital V with respect to K. And under this transformation X, coordinate X, go to X minus BT. So that would be X, our X prime. T doesn't change under Galilean invariance. So this Galilean transformation, the Galilean transformation transformed the fluid. We can think about, so the Galilean invariance allows us, what it allows us to do is it allows us to interpret, right, volume of fluid, which previously is characterized by epsilon, like n epsilon pi, as a boosted volume of fluid, boosted to a certain velocity, something at rest, and then boosted, Galilean boosted to velocity V. Okay. So this fluid, piece of fluid that is at rest has zero momentum. Momentum density in this place is zero, and it has non-zero n and epsilon. It can be non-zero. And so using the rule of Galilean transformations, which we talked about the previous time, we can map the conserved quantities in the original moving volume of fluid to the fluid at rest, moving with boosted velocity V. Okay, so the formula that we will have here is that n is equal, n is the same, on the n is n. So I will even not use a different formula for the density at into two frames. The pi, the density of momentum in the lab frame. So everything here is in the lab frame. Using Galilean transformation, pi in the lab frame is related to the velocity, like mn times v or rho v. And the epsilon in the lab frame, which I call epsilon, the density of energy, capital epsilon, is rho v squared over 2 plus the epsilon. This epsilon is the epsilon in the rest frame of the fluid. This equation is pretty trivial in its physical meaning. It just says that the total energy is the kinetic energy, rho v squared over 2, plus the potential energy, epsilon. It's the energy that is not, well, when we say this potential energy, actually it's both the kinetic energy of the random motion of the particles and the interaction energy between them. So what we separate out is just the energy associated with the average motion of the whole volume. There is also some extra condition, let me call it Galilean invariance. Plus, that's not properly Galilean invariance, but it's required that all our particles have the same mass and they do not have internal degrees of freedom. This Galilean invariance plus tells us that the particle number current and the momentum density are related by an exact relation, which originates from their microscopic dynamics. So, for example, in terms of the quantum mechanical operator, the momentum density is written in second quantized form like this, where psi and psi dagger are annihilation and creation operator, and J is the same, but it's over 2 with I over 2m times the same thing. So that are the conditions that we have to impose. So this one actually its effect on hydrodynamics is immediate. It eliminates one of the things that we have to do. One of the constitutive relation is completely fixed. It's fixed one constitutive relation. That is, now J is just 1 over m times pi. Exactly. There's no other wiggling room. Okay. Okay. So at this step, then let's summarize what we have done at this step. Then we have this following equation: d over dn plus grad of 1 over m pi equal to 0. All right. Second equation, but pi is rho v. Okay, so let me write this equation like d rho over dt plus grad rho v is equal to 0. So I multiply this by m and also use the formula that we obtained from Galilean boost, pi equal rho v. The second equation is equation d over d rho v I plus del d j pi I j equal to 0. And the third equation, d over dt, the total energy, rho v square over 2 plus some internal energy epsilon. That's the energy in the rest frame of the fluid plus grad j epsilon equal 0. Okay, any question so far about this? Okay. Okay, now I'm going to explore Galilean invariance further. Actually, what we have done here with Galilean invariance is just one small, simplest application of Galilean invariance. So Galilean invariance actually imposes a more stringent conditions. Basically, it says the following. So Galilean invariance allows us to take one solution to the system of equation and derive an infinite number of other solutions by Galilean boost. So we can go from one frame to another frame. It's exactly the same configuration of the flow of liquid, but described in two different systems of coordinates. So in mathematically, it means that from one solution, we have an infinite number of other solutions, from another solution, which can be thought of as the first solution boosted by a volume, by a velocity v. So let's see how that boost acts on the how we can get, what does it mean that we can get from one solution to another. So suppose I have a solution. Let me write it, a solution that is characterized by some density t x, some velocity, say t x, and then say energy density t of x. Right? This is small epsilon. That means energy in the rest frame. So let's look at this rho first. So under the Galilean boost, from rho we can get another configuration. Let me call that rho prime. Defined so that rho prime at time t coordinate x prime is equal to rho at time t in coordinate x. Okay, where x prime is equal x minus vt. V is capital V. That is the velocity with which we have boosted our system. It just means that we are dealing with the same configuration in two different systems of coordinates, but we can also think about this more mathematically. We can say that there is a new configuration. So here let me write this way, since this x prime is x minus v times t, so I can write rho prime at tx at the same place. X now is equal rho 3x plus v times t, which means I can I now have a new field at point x time t. Its value is equal to the rho of the old field configuration at time t and x plus vt. Okay, so now with the same with the epsilon. Epsilon is something that does not depend on the frame. By definition, this epsilon, the small epsilon, is the energy of the fluid in its rest frame. So it doesn't depend on the frame. It also has to have. We can also write this epsilon in a new frame. The only thing that changes here is the coordinates at which this function is evaluated. This v is somewhat different. When we go from one frame to the other, let's do it a little bit more carefully. V prime, we know that v prime at tx prime should not be equal to v at tx, but it has to be minus, we have to subtract v from that. It's just the velocity transformed more non-trivially under Galilean boost because it's a velocity. And so that from that we find also v prime of tx is equal v at tx plus vt minus v. Okay, so these three equations allows us to go from rho to a new rho prime, epsilon to a new epsilon prime, and v to a new v prime. And our condition on our hydrodynamic equation is that if these are, if rho epsilon v satisfy the hydrodynamic equations, rho prime epsilon prime v prime would need to also satisfy the hydrodynamic equation. That is the meaning, the full meaning of Galilean invariance. If we can impose that, then we can be sure that we have exhausted all the conditions from Galilean invariance. Any question so far? Okay, so let's, yeah.
I have a quick question about the lane invariance that we introduced in the very beginning, considering that element of fluid. Is that a local boost that we're considering, or is that a?
It's a global. It's a global boost. So in order to, so here, right? You're saying.
Mm-hmm. Yeah,
here
exactly.
I'm saying that in order to characterize a certain volume of fluid, I characterize, well, I use the parameter I call V, which is equal to the parameter of a global Galilean boost, in which frame the local momentum density is 0. So here I avoid using local Galilean boost.
Okay, and okay, thank you.
Yeah, it's possible to do local Galilean boost. It's a whole different formalism. Okay, so here I have these conditions on the invariance of the equation, and now I can look at the equation and see if they are invariant and what conditions should I impose to get this invariant. So for example, let me look at this the first equation. D rho, my first equation looks like this: d rho over dt plus grad divergence of rho v equal to 0. So here rho now move to a new rho prime, which is equal to the old rho, but evaluated at x plus vt. That means when I take time derivative now, it's d over dt of the new function rho prime is like d over dt of the old function, but this dt can act either on this t or this t. That means that my dt prime, rho prime, is like dt rho plus d over dx over dt, that is v dot d rho over dx t. Or I can formalize it like this: as a rule, under Galilean boost, my time derivative has to change. My time derivative becomes linear combination of time and spatial derivative, because the spatial coordinate in the new solution depends on the time. Speaking. Okay, so now this first term d over dt of rho under this Galilean boost becomes dt plus v cross gradient times rho. Okay, so now the second term, gradient of rho times v. So when I take gradients, it's a spatial derivative. We can look at this and see that the spatial derivative doesn't change under Galilean boost, so I don't have to worry about this gradient. The only thing that changes is the velocity. Velocity is shifted by minus v. So it's gradients of rho v, divergence of rho v, but divergence of rho dot v is constant. You do a global Galilean boost everywhere with the same velocity, so this becomes minus v gradient of rho. So this means when you look, you sum up these two contributions, you see this one and this one cancel each other. So the each term in the continuity equation, or conservation of particle number, changes, but the whole equation, the whole left-hand side of the equation remains unchanged. So this equation is Galilean invariant. No problem with that. So that's the first equation. Now let's look at the second equation. This is now more informative because we have some unknown, this flux of momentum along the some direction that we call pi ij. Okay, this momentum flux, this pi ij, is also called stress tensor. We will call that a stress tensor. So now let's do a Galilean boost. This derivative with respect to t becomes dt plus v times gradient. So but now there are indices, so let me write explicit indices. Vj. By the way, if I write upper and lower in this index in the vector tensor, it's the same thing here. Times rho vi minus rho vi. So that's the first term. And then, of course, we don't know how this thing will go, but it is some boosted to momentum v. So our task is to find out how this pi should transform under boost. So to simplify our calculations, we can just restrict ourselves to small v. So that means infinitesimal boost. And ignore terms of order v squared that we obtained. Keep only terms that have no derivative. So that was our original things. And then term with 1v, with 0v, with 1v. So there is one, the one that I can see here, this v, j, dj, act on rho vi, and then this dt act on rho vi. So vi times dt of rho. Was the thing that I don't know yet because they are related to stress tensor pi. Derivative of rho, you can use the continuity equations to write this as vi dj rho vj with the plus sign. So that means that whatever this pi is, it's transformation. What do we get? That is this. I'm saying the change of dj pi ij that we want has to be such to cancel the two terms that we have just obtained. Okay, so now one term where we know. So in particular, let me say it this way: we can guess that pi ij. We can separate out one part of pi ij where that property is satisfied. So let me write pi ij is equal rho vi vj times some pi prime, whatever, like pi ij, the rest of that. You can check right away that this pi ij transform in such a way that to cancel these two terms. So because v got minus capital V under Galilean boost, the change of pi ij will be minus rho vi vj minus rho vi vj plus change of delta prime, and you take derivative. It's exactly what you need, the first term. So if we separate out rho vi vj from the stress tensor pi ij, we have we need to only to require that pi prime is just equal to pi ij at say t x plus vt. Doesn't have anything else under its transformation law under Galilean boost. So we sometimes say that this pi ij prime has to be invariant under Galilean transformation, that it doesn't have this shift like the velocity would shift under Galilean boost. So using Galilean invariant, we can single out one particular contribution proportional to the velocity, this by vi vj in the stress tensor. In particular, this pi prime now has a very restricted structure. This pi prime ij, if I have just a tensor, right, I would be free to write in the constitutive relation for pi ij prime something like a vi vj. But this is forbidden because we know that pi prime ij is invariant under Galilean boost, Galilean invariant. The only thing that we can write is something times delta ij. Assuming that now we have an assumption next, an assumption of isotropy. So if the system is isotropic, the only thing we can write in 3 dimensions, the only thing we can write is epsilon ij times some function. We call that p. This would be some function, some thermodynamic well, sorry, let's think about this. So when we write the when we write down constitutive relations, we have terms. We organize this constitutive relation in power of derivatives, okay, and pi prime ij can be also be expanded in terms of the number of derivatives. So if I have here terms that have no derivative, then this p has to be a function of like t and mu only. Cannot be any cannot be a function of v square, for example. It would violate Galilean invariance. And then we can write term with one derivative. So in term with one derivative, we can exclude this, for example, this kind of term. Vi dj rho would not be possible, exactly because v would not be invariant under Galilean transformation. So with one derivative, the only thing we can write are some derivative of velocity, like the divj type of term, or djvi, or again delta ij times total derivative, total gradient of v. These would be the structure that are allowed by Galilean invariance, because, well, v changes under Galilean transformation, but its derivative doesn't change. Capital V, the parameter of Galilean transformation, is constant. So all this stuff we will talk about a little bit later. I'm not going to introduce three different coefficients for three of them, but I'm going to write this as tau ij. These are the first derivative of velocity. These are proportional to first derivative of velocity. Maybe times some function of temperature, times some function of temperature and chemical potential. So the Galilean invariance allows us to write down the constitutive relation. So let me summarize. Let us summarize what we have found here. Pi ij has to be equal rho vi vj. This rho is just the density of particle plus some delta ij, some p, which is some function of t and mu, and then plus term with first derivative tau ij. Any questions so far? Okay, so now let's proceed to the next conservation equations. Plus the gradient of j epsilon is equal to 0, and see how the how do we get the how the Galilean transformation acts on this equation. So time derivatives again becomes, so maybe I still use the indices. Make sure this good. Now I have this rho v squared over 2 plus epsilon, but v change under transformation, Canadian transformation. V shifted by capital V. I'm only working at linear ordering V, and so I have this VI, I'm sorry, with minus sign. Yeah, minus sign. Okay, plus that epsilon prime in the new frame have to be equal to 0. Okay, and so the first term, what do we see? The first term, we see something like VI, VJ, DJ, the change under Galilean boost, ignoring the term that already in there in the original equation. Bring down the things linear in V. Now Vj rho V square over 2 plus epsilon. And then d over dt of that minus Vi d over dt rho small vi. But that I can use the conservation for momentum to rewrite as plus Vi dj pi ij. I think I've been consistent with the way indices is located. So our goal is to find some structure that we can separate out from the energy current to cancel this contribution to the I'm sorry, there is another one. This is not just that. Plus Vi dj rho. Oh, I'm sorry. It's actually only this. But I can rewrite this as Vj dj rho v square over 2 plus epsilon, taking into account my knowledge of the constitutive relation of the stress tensor. Right, is Pij plus tau ij. I want to get the constitutive relation for J, consistent with Galilean invariance. And I know inside this energy current, there must be something that transforms to cancel this piece. And it's easy to guess what it is. It is the following structure. Rho v square over 2 plus epsilon times v J epsilon J, sorry for this index is Vi, Vj plus, let me write this way, V P delta ij plus tau ij. And then I can write whatever is left is some prime, j prime. You can see, you can check that if you do a Galilean transform on what I've written here, the Galilean boost, simply shift the velocity, shift this v, you cancel all these terms. You shift Vj by minus capital Vj, you cancel that term. Inside here, here is rho v square. You shift that v here, cancel out this term. So this last term also cancel that term here. Okay, so if one separate these terms out, we find that we can, the requirement on Galilean invariance now becomes simply that this J prime has to be Galilean invariant. It's unchanged under Galilean boost. So it's unchanged. Unchanged means that only the coordinates change, but there is no addition to that tensor. Any questions so far? So let me write it. Summarize
sorry.
it. Yeah.
Could I ask a quick question? So like, I'm wondering, like, is there any case like we can consider the derivative order higher than first derivative?
So here I'm constructing the hydrodynamic theory to first order in derivatives, and so this term in this constitutive relation, actually all the first derivative terms appear only here. So here is the only here I have first derivative. So there's no term of proportional to first derivative anywhere in this first two terms. I don't completely understand your question. So you ask whether we can push this formalism to second derivatives, to include second derivatives?
Yeah, or higher derivative, something.
So hydrodynamics, if naively we do it, you can think about the all this constitutive relation as expansion of a derivative. There is leading order in derivative, the first derivative term. And it's tempting, it will be tempting to push further. But I hope later to show you that actually in the real world, due to the presence of noise, hydrodynamic noise, these second derivative corrections have little physical meanings. The noise actually overwhelms, in some sense, these second derivative terms.
I see, thank you.
Yeah. Okay, so that we can write this way. So in the energy current, there is basically something that flow with a velocity v plus vi tau ij plus some term with first derivative. Let me write like qi. Qi is term proportional to first derivative. First derivative of what? At this moment, it can be, so for example, derivative of temperature, derivative of chemical potential. Doesn't have to be. Cannot be derivative of velocity because that would have a wrong number of indices. Okay, so now that's everything we have done is, I think we have exhausted the power of Galilean invariance. Satisfied? So it remains to us to figure out the structure of these terms with first derivatives and figure out how many possible kinetic coefficients we can write, how many independent kinetic coefficients, that is the coefficient of these, how many first derivative structure we can write down. And that requires an analysis of entropy productions. So let me just outline what we have to do. I'm probably not going to do this in the full, or I'm not going to follow all the technical details of the calculation. It's actually quite straightforward. What we do is to write down all our equations. Rho vi plus like bj, rho vi vj plus p delta ij plus tau ij equal to 0. Then d over dt rho v square over 2 plus epsilon plus dj, that's rho v square over 2 plus epsilon plus p vj plus vi tau ij plus qj equal to 0. And try to find out the from these equations how much entropy is produced in the system. The entropy production can be computed from this equation because of the presence of this derivative of energy with respect to times. Here, this energy epsilon, remember this epsilon is the energy of the system, the internal energy, the thermal energy that is not related to bulk, is fluid motion. And so the epsilon over dt, can write this as using the first law thermodynamics. TdS, dE is TdS plus mu dN. So the epsilon over dt is dS over dt, and you can actually do certain, take some linear combination of these equations and single out the terms, single out this term. So for example, you need to multiply this equation by mu and then subtract it. To subtract the mu dN over dt of this equation, we'll take this equation with sign plus, take the first equation multiplied by minus mu, and then in the general form, you actually need also to use the second equation. I'm not going to do the full calculation, but I'm going to just illustrate how that's done. Let's go to, it's actually, one can simplify this equation by using a trick that's quite popular in general relativity. That is, we do the calculation in the frame where our velocity at our given time in x. So at the time in the coordinates where we are interested in calculating is 0. It's always, we can always choose the frame in which the velocity at a given place is 0, right? In the neighborhood, it will be not 0, but in our given point where all the formulas are written, the velocity is 0. Velocity 0 means only v is 0. It's the derivative of v is not going to be 0. Both the time and spatial derivative is non-zero. But in fact, that trick makes the equation simpler. So for example, the first equation becomes dn over dt plus n grad v is equal to 0 because the just because v is 0. If we derivative acts on n, then it's multiplied by v, it will give us 0. So now I don't think I will need the second equation. The third equation looks something like this: the epsilon over dt, right? Because derivative acting on one of these v square will kills only one v. The other v would give you 0. Okay, and then here I have something like plus, like epsilon plus p grad v, right? And then I have plus dj vi tau ij plus dj qj equal to 0. That's basically what the two equations are, right? And then I need to fashion these two equations into an equation of conservation of entropy. That means multiplying this equation by minus mu, and then add to the second equations. And after calculation, you see that the equation for conservation for production of entropy looks something like a T ds over dt plus it would be something like epsilon plus p minus mu gradient of v, right? And then plus something like equal like djvi tau ij plus minus djqj equal to 0. Oh, sorry, equal. So so you see here, it already looks something like, if you divide that equation by t, it looks exactly like the conservation, the production of entropy, like ds over dt. We expect that the conservation law for the entropy is like ds over dt plus gradients of s v plus something. There might be some correction, is equal larger equal to 0, right? This is it almost has this form of that. So we have to require that is epsilon plus p minus mu n divided by t is equal to s. To have this s in this equation. This s in the equation actually can be argued that it's also required by Galilean invariance, or in the, you can see it in the full calculation. It's the only thing that can appear here is s, and so this p is completely fixed. It's not something that we can choose in the. It's part of the constitutive relation, but it has to be a thermodynamic function that is mu n plus st minus e minus energy density. In other words, it is pressure. It has to be pressure. It cannot be nothing else than pressure. So this P that we have introduced as just a notation in the equations is such as pressure. Now this is pressure. We know that it's pressure. Another thing that we also know is that the total production of entropy Vj Vi tau ij, right, minus djqj is have to be larger or equal to 0. And any questions so far? So at this step, there is one thing that we want to clarify. So this tau ij must be such that it contains derivative with respect. So let's recall how it appears in the stress tensor. Stress tensor has this Vij plus P delta ij plus tau ij. It's a tensor with of second rank. And any tensor of second rank can be decomposed into symmetric, anti-symmetric, symmetric traceless, anti-symmetric, and the traceless part. So write down. Okay, so there's one strange thing you can write here, that is anti-symmetric contribution to the stress tensor. In principle, at this moment, this is rotational invariance, Galilei invariance completely allowed such a term. This term would be the only anti-symmetric part of the stress tensor, anti-symmetric component of contribution to the stress tensor. So let me show you that this is not allowed. It's actually, one can show that this is not allowed. If it was allowed, that would means that if the fluid rotate, this is simply the vorticity of the fluid motion. It will be non-zero if the fluid move in a vortex-like manner, like this. If such a term is allowed, that means that even when you take a cup of water and then rotate it rigidly, there is a contribution to the stress. So let's let me show you that is not possible. And that comes from conservation of angular momentum. Conservation of angular momentum means that we have some quantity that we call Mij. So Mxy would be the angular momentum along the z direction. So it's an integral over dx of xi pi j x minus xj pi I of x. And nothing else. So here it's an assumption here is that the only contribution to the angular momentum comes from the motion of the fluid. The particles do not have internal degrees of freedom that carry angular momentum. So if we require this is 0, that is dx xi d pi over dt minus the same with I and j exchange. But we have here the constitutive relation. This is equal dk of pi j k, all right? And then we do integration by part. The integration by part give us dx delta ik, so that will be pi ji minus pi ij. So if that we put this in, everything pi ij is symmetric everywhere, but here the only term that is not symmetric is this xi term. So that would be xi up to some constant, like I think it's like -2 or something, minus xi times di. I'm sorry, that would be, this guy has to be inside. Xi has to be inside. And then I have the ibj minus djvi, right? The ibj minus djvi. That has to be 0. C is some function, some kinetic coefficient. V is something we can control for, this is just the initial condition for our flow. The only way I can think of where this is 0 is when xi is a constant, independent of temperature or chemical potential. But that is very strange. We have a kinetic coefficient that does not depend on the particle density. If I can't. In fact, when preparing this lecture, I cannot think of any general argument that this constant has to be 0. But it looks like it has to be 0. Otherwise, very dilute gas with almost 0 density would have the same kinetic coefficient xi compared to a gas with finite density. So I wonder if anyone has encountered this. I should have known that, but I think this from this physical argument, I can say I wasn't able to find rigorous a simple symmetry-based argument to say that this xi has to be 0. But I think this xi has to be 0 based on physical consideration. So
I have a quick question regarding how you conclude that xi must be constant. it seems like what you did is you performed some integration by parts.
Yeah.
Is
Uh-huh.
that correct?
Yeah.
Are you explicitly assuming something about what's happening at the boundary of this domain when you do that?
I assume that I don't have a knowledge about the domain, because the knowledge about the domain will have to be added onto this equation as either some boundary conditions or some extra stress term or something. I assume I don't know this. I think I was approaching a better derivation, but it required putting this fluid onto a 3-sphere that doesn't have a boundary. Yeah. Okay, so let's assume that is 0. When you look at the how Landau and Lifshitz treat that, they say if I take a rigidly rotating, if the fluid rigidly rotating, obviously there cannot be any contribution to the stress. But it's not very clear to me that it's obvious. There can be a stress that is constant over the whole place, and we just don't see it because the stress appears in the equation as the derivative in terms of the derivatives. Okay, so let's.
It's also unclear, that argument. I mean, it's factually false. If you do rotate something at constant, that there would actually be a dimple on the surface of the thing, because there are stresses that have to balance the centrifugal forces. So it's
yeah. So inside, we say the stress. It looks like the argument one is based on the statement that inside this fluid, things rotate around each other. It cannot be a stress, but I just don't see how to make that argument. How can you get this argument honestly? Okay, so now if that is assumed to be true, then we have our final finally what we can say is that the positivity of entropy production, that is here, allows for, after you have analyzed everything, you find that it allows for 3 kinetic coefficients. Where do I write it? Here. This, and another one in the equation for Q, the extra term in the energy. So it is Q. And here is my third equation. So this is eta C zeta kappa, 3 kinetic coefficients. One, 2 related to the stress generated by the inhomogeneity or the differential flow, and these are called viscosity. So this is called the shear or first viscosity. This is called bulk or second viscosity. And this is the thermal conduction, thermal conductivity. There is only 3 possible kinetic coefficients, and all of them have to be larger or equal to 0 based on the conditions of positivity of entropy production, and also there's no, so now in this particular case, there is no extra condition that arises from Onsager relations. Next time, I think we're going to finish this discussion, and I want to tell you a little bit about what kind of modes that arises from these equations: this shear, sound, and thermal diffusion. And then we think we are going to talk a little bit about the ideal fluids, about some properties of solution to the equation of motion of an ideal non-fluid where all the kinetic coefficients are set to 0. Okay, let me stop recording.